Good morning, everyone. Myself, Assistant Professor Sandeep Shah, working at Technocrats Group of Institute, Bhopal. So today we are going to start new chapter, that is the convection heat transfer. So this is the table of content, and we will discuss one by one. That is introduction of convection heat transfer. Second is free and forced convection. Third one is thermal boundary layer concept. Dimensionless parameter, evaluation of convective heat transfer coefficient, and then we will discuss forced convection and principle of Reynolds analogy. So first we will discuss what is the requirement for convection heat transfer. So the first thing which we have to consider is the solid and fluid interface, and the temperature difference between solid surface and surrounding fluid, and fluid should be in motion. And what is the mechanism of convection heat transfer? That is mechanism is simple, that is the temperature difference. There should be the temperature difference between solid surface and the surrounding fluid. So here let us suppose that this is the wall having temperature TW, and fluid flowing temperature is T infinity. So there is the temperature difference, that's why heat transfer will take place. Now, what are the various types of heat convection process? That is the free and forced convection. In case of free convection, the heat transfer takes place just because of the density difference caused by the temperature gradient, and in case of forced convection, there is external medium which is responsible for the flow of fluid. The next which will differentiate between types of flow is laminar and turbulent flow. So as we know that this convection heat transfer just because of fluid flow, so we have to consider type of flow of fluid also. So we know that in case of fluid mechanics, if fluid is flowing over a surface, so we are having two types of flow, that is laminar and turbulent, and this is just the type of flow will also decide the rate of heat transfer. So in case of laminar, there is no intermixing of fluid. Only laminar, only streamline flow will be in case of laminar, but in case of turbulent, macroscopic mixing of fluid particles will take place. So now the next concept is also regarding to the fluid flow phenomena, that is the boundary layer. We know that if fluid is flowing over a surface, then what will happen? The boundary layer concept will take place, that is the boundary layer formation is taking place. That similar to boundary layer, hydrodynamic boundary layer, we also are having thermal boundary layer. So here in case of the hydrodynamic boundary layer, we know that due to the velocity gradient formation, there is a thin layer of fluid formation taking place, just because the fluid layer to the surface is at a lower velocity than the fluid flowing at the free stream velocity. So that's why the boundary layer, due to velocity gradient, the boundary layer taking place. So similar to this, due to the temperature difference between surface and fluid, the thermal boundary layer will also formed, and this is the thermal boundary layer profile. That is, we can observe here that plate having temperature TW is greater than the fluid flowing temperature. That's why the temperature, due to the temperature gradient, we are also getting a thermal boundary layer profile here. So to understand or to study the convection heat transfer phenomena, we have to study also some dimensionless parameters. That is, the first one is Nusselt number. The Nusselt number is a dimensionless quantity defined as HL upon K, where H is the convective heat transfer coefficient, L is characteristic length, and K is thermal conductivity of fluid. So Nusselt number will be defined. Why this is important? This is just a physical. Nusselt number could be interpreted as a physical as the ratio of temperature gradient in the fluid immediately in contact with the surface to a different temperature gradient Ts and T naught upon L. So this is the profile which we are having the temperature gradient due to the temperature gradient, temperature distribution in a boundary layer, and it is also known as Nusselt modulus. So to calculate the rate of heat transfer, we will also use the formula of Newton's law of cooling as we have discussed in the previous chapter. So here heat flux, that is the Q upon A is equals to H TW minus T infinitive. So similarly we can have Nusselt number equal to HL upon K. So heat transfer convection involve conduction and mixing motion of fluid particle. How? Because the solid surface, the fluid in immediate contact to the solid surface will have conduction mode of heat transfer, while the fluid away from the solid surface will be heat conducting due to convection. So the rate of heat transfer coefficient will be calculated by using this formula, that is minus K dt upon dy upon Tw minus T infinity. So the next number is the Grasshopp's number. As we in case of fluid flow, we differentiate type of flow by using the dimensionless term Reynolds number. Similar to here, in case of heat transfer, the type of flow, that is the free convection, and in case of free convection we will use the term Grasshopp's number, and it will be used to differentiate between the type of flow. That is the turbulent. In case of turbulent flow, we are having Grasshopp's number value is greater than 10 raised to power 9, and for laminar flow Grasshopp's number is less than 10 raised to power 8. So this is the formula which will be used to calculate the Grasshopp's number. The next dimensional parameter is the Prandtl number. The dimensional parameter, basically it is given by mu Cp upon K is equals to mu upon alpha. Here mu is dynamic viscosity of fluid, B is kinematic viscosity, alpha is thermal diffusivity. So the number assumes significance when both momentum and energy are propagated through the system. It is a physical parameter depending upon the property of medium. It is a measure of relative magnitude of momentum and thermal diffusivity. So now the next term is the Rayleigh number. Rayleigh number is nothing but it is the product of Grasshopp's and Prandtl number. So now the main aim is to calculate or evaluation of convective heat transfer coefficient, that is H. There are having two different ways, that is dimensionless analysis and actual solution of momentum and energy equation. So the first we will use analytical solution. So by using this formula, that is the Nusselt number formula, here we are having two types of Nusselt number, that is local Nusselt number and another one is average Nusselt number. So Nusselt number is a function of Prandtl number and Grasshopp's number, and so by using this formula we can calculate the Nusselt number, and we subsequently we will find out the value of heat transfer coefficient. So this is example numerical problem. We can here see that a large vertical plate 3 meter height and 2 meter wide is maintained at 75 degrees Celsius and is exposed to atmosphere at 25 degrees Celsius. Calculate the rate of heat transfer. So by this is the solution. You can here observe by this. Now the next is the forced convection heat transfer principle. So as we have earlier discussed about free and forced convection, that is the forced convection requires the external forces in the form of pressure difference, that is like a blower or any other compressor required to make the fluid into motion, and it could be either laminar or turbulent, depends upon the relative magnitude of inertia and viscous forces. So Nusselt number is a function of Reynolds and Prandtl, and we can use this formula. Principle of Reynolds analogy. So Reynolds was the first person to observe that there exists a similarity between the exchange of momentum and exchange of heat energy in laminar motion, and for that reason it has been termed as Reynolds analogy. So Reynolds analogy basically given by here new term Stanton number, that is Stanton number is nothing but result upon Reynolds into Prandtl, Cfx upon 2. Cfx is the skin friction coefficient. So again, this is the one important numerical problem. You can study and your concept will be clear. Okay, thanks.